Okay, welcome everybody to another Origin seminar. Today we have a talk by Kevin Wagner, who did his PhD here at the University of Arizona, working on direct imaging in the research group of Daniel Apai. And he's currently a NASA postdoctoral Hubble Fellow working on imaging low-mass planets with the LBTI. And today he's going to give a talk about imaging low-mass planets with NIR, which is an exciting project. Also, as a short reminder, please try to keep your questions to the end of the talk. If you have a very urgent question, please put it in the chat. And if possible, please stop your video of yourself to save some bandwidth. Okay, Kevin, take it away.
All right, hi everybody. Thanks for joining. I'm excited to be here. Well, I am in Tucson, but I'm also excited to be at Origins virtually and happy that all of you joining virtually with us are able to do so. So I think it's useful to keep this overarching question in your mind throughout this talk, and that's how close are we to imaging a second Earth? So here I've pictured an image of, well, our own Earth, and this is the pale blue dot image that Carl Sagan popularized and which you're all probably familiar with, taken by the Voyager spacecraft as it was on its way out of our own solar system. And I think this is a nice place to start because this is also what we should expect to see when we actually get an image of another Earth-like planet around another star. Everything that we learn from that planet, we're going to have to learn just from looking at this one single point of light. So now let's take a step forwards to the state of the art of current exoplanet imaging. So this video on the left shows a video of 4 super Jupiter planets in orbit around the young star HR 8799. HR 8799 is about a 40 mega-year-old star, so it's less than about 1% as old as our own sun. And these planets that you see here, you actually see in thermal emission. And well, these planets are rather hot. They're around 1,000 or 1,200 Kelvin or so each, and this temperature is gained from energy that was gained during their formation phase during their hydrodynamic collapse. And since planets don't have an internal engine or internal heat source, they cool over time. That's what's being shown on the right. These are 2 different classes of models of planetary luminosities evolving with time. These form essentially bracketing cases. The dotted lines here are what are known as the hot start models. The solid lines are what is known as the cold start models. You can think of these as essentially extreme cases of either planets where you start them off so hot that if you add a little bit more energy, they cool so rapidly that it doesn't really make much of a difference. Or in the opposite case, the cold start planets are essentially as cold as you can imagine having them, to the point where they're in equilibrium with the midplane of the disk. But in any case, the important thing about these models is that they cool over time, and that if we want to image mature planets, we're going to have to look at planets that are in equilibrium with their stars and no longer planets that have any memory of their initial conditions or heat left over from their formation. So this is putting that into a series of black body spectra now. So those young planets that I just talked about, like HR 8799, correspond to about this gray range here of around 1,000 Kelvin. The peak of their luminosity is at around 2 or 3 microns, so best observed in the near infrared. Our own Jupiter today is cooled down to around 1,000 Kelvin, just as a aside. And if we want to look at planets that are in the habitable zones, these planets are going to be at around 300 Kelvin or so, or approximately room temperature, or the temperature of the Earth today. And for these temperatures, the wavelengths, well, these temperatures correspond to peak emissions at wavelengths at about 10 microns. So in other words, habitable zone planets are, the contrast between a habitable zone planet and its star is minimized if we look at the peak of its emission spectrum here at about 10 microns. And we can create a simple model for the temperature of these planets and then the brightnesses and luminosities that we should expect just from these assumptions of radiative thermal equilibrium. So briefly, the equilibrium temperature of the planet is proportional to the temperature of the star, also to the radius of the star to the 1/2 power, its average orbital separation to the -1/2 power. It's a weak function of the albedo, or the amount of light that's reflected away. And then for the models that I'm going to be showing you later on in the talk, we included this extra parameter here, this 1 + F extra, to include a little bit of extra heat For instance, from the Earth, this is gained from the greenhouse warming effect. If we were to look at the Earth in 10 microns, its temperature is about 10% brighter than what we would expect it to be in radiative thermal equilibrium. So this is a pretty simple picture. This ignores things like molecular absorption, but this is okay for our purposes because we're looking in regions of the spectrum and filters where there's not much absorption expected. And also, we don't know exactly what we should expect for the albedos. We don't know what we should expect for the amount of extra heat, and these tend to cancel each other out. So we try to make some rather appropriate assumptions here and don't get lost in the specifics of what actually the constituencies of the atmospheres are. So that's the motivation of why we would want to look at planets in the mid-infrared. Is this is where their contrast with respect to their star is minimized and where this might be the most favorable. But it's also rather challenging. So here again is the HR8799 system shown on the left in 5 microns and on the right in 4 microns. And you can see already that the planets are, well, much more difficult to pick out in the case on the left in 5 microns. And this is only a wavelength that's 20% longer than 4 and not, well, still a factor of 2 away from what I was just suggesting that we get for at 10 microns. So you can see that the background everywhere in the image has been raised. B is the less confident detection, and so on. But also the beam diameter is larger as we go to larger wavelengths. So the speckle pattern in the center from the star extends to larger distances. It's even kind of questionable whether or not E is seen here. So these are the main challenges that we're dealing with in the mid-infrared is that, well, of course, our angular resolution is becoming poorer, but also probably more importantly is that we're dealing with much larger sources of background. But let's take a look at what we could achieve if we were to, say, double the wavelengths of this image on the right and go towards this peak wavelength of around 10 microns, what we might expect these planets to look like. So again, these are the models that I described earlier, just coming from that simple assumption of radiative equilibrium. These have about 10% heat added to be similar to conditions of the Earth, and also albedos of about 0.3 to be similar to the Earth and also other solar system planets. Progressing from the top to the bottom here, the lines correspond to planets with radii equivalent to about Jupiter and Saturn, then Uranus and Neptune, something like a super Earth at about 1.7 Earth radii, and then an Earth-like planet. And of course, at various separation.
Kevin, we have a question from Andrew, who asks, isn't the greenhouse effect still radiative equilibrium, just not a black body?
I'm not sure that I totally understand the question. So let me perhaps rephrase and say that if you were to look at the Earth in 10 microns, what you would be seeing is, well, you'd be looking through an opacity window and seeing more of the warm surface rather than the upper layers of the atmosphere, which would be cooler and more in thermal or radiative thermal equilibrium. So I hope that answers, and perhaps if it doesn't, then let's come back to it and discuss more later on. Okay, yeah, so if another question hasn't popped up by now, I assume we can just talk a bit more later on.
Yep, please continue.
So the black lines here on that are lower than the red lines show the wavelength range that I just showed you, this image of HR8799, and on the left, so this is the M band, or about 5 microns. If we were able to double the wavelengths that we're observing in to about 10 microns, or the N band, you can see that all of these planets are about 1,000 times brighter. So well, brighter in terms of contrast with respect to the host star. And this actually brings them up into ranges that are rather achievable. So something like 10 to the minus 7 to 10 to the minus 4 for solar system sized planets in the N band, compared to something that's, well, quite a bit more challenging of 10 to the minus 10 to 10 to the minus 8 for 5 microns. So if we were to look at this in 10 microns, of course, this is rather challenging because of the reasons I described with the angular resolution and much higher background. But if we could do this, we could potentially take advantage of this fact that the contrast between the planets and the stars is 1,000 times more favorable between these two wavelengths. So let's compare again to some state-of-the-art exoplanet imaging sensitivity limits. This is a 2 micron observation done with SPHERE on the right of Sirius, which is similar in brightness to Alpha Centauri A. The top curves that you see here and the dotted dashed lines in red and blue show the performance of a previous AO system. So rather the difference between the lines on the top and the bottom show the progression of the field over about 5 to 10 years. What I want to draw your attention to, though, is just a similar range in the plots to get some sort of grounding of what's been achieved versus what we're proposing to do here. So on the left, again, this is not a sensitivity diagram. These are our models for the brightnesses of these planets as a function of their separation. It just kind of happens to also look like a contrast curve, or well, a sensitivity contrast curve. But now, with the same region highlighted here of contrast of about 2 times 10 to the minus 7 and separations of about 1.2 arc seconds, this is something that actually has been achieved with SPHERE. So what I'm proposing is, well, let me be clear, it's still quite a bit more challenging to achieve contrast this extreme in 10 microns. And this is the question that we set out to answer, whether or not we can even do this. But I think it's motivating to see that we've at least achieved these sensitivity limits at some wavelength. So now the question is whether or not we can extend this and do something similar in the mid-infrared. And just with a one-to-one comparison, if we were to be able to do this, we would already be somewhere in the sub-Neptune range for planets around Alpha Centauri. All right, so just to reiterate, this is what our goal is. So this is an image of Alpha Cent A and B taken with HST, which of course is different than the VLT. It's not looking in the mid-infrared, but it's also has a smaller diameter. So we actually end up with something like a comparable angular resolution here. So what we want to do is we want to image the habitable zones of these nearby stars, which correspond approximately to these ranges that I've indicated here. And what we want to do is to be able to reduce the noise in this region to the level at which we're able to see planets that are something like what we would see in the solar system, hopefully even something that might be a rocky planet or super Earth-sized planet. And in the future, to, of course, push down to what we really want to look at, which would be Earth-like planets. And this noise has 2 different components. One of them, which you see dominating in this image, is the noise from the star. But there's also background noise that's present throughout the image. And of course, if the background's higher than the speckles of the star, then, well, you would be in the background limit. But this is the game that we're trying to play, is to reduce the noise in the habitable zone enough so that we can see the planets that are around Alpha Centauri in thermal equilibrium. And again, this light that we're looking at from the planets is not reflected light, the light that the planets are emitting themselves, similar to a black body. So any questions there? Take a drink, and since I haven't heard anything, I guess we can continue. So this is what our team set out to do with what we call the NEAR experiment, or New Earths in the Alpha Centauri region. So this is a 100-hour campaign with the VLT to try to achieve this goal of imaging planets within the habitable zone of Alpha Centauri. And more broadly speaking, just to see how far we can actually push mid-infrared imaging to see what sort of sensitivities we might be able to achieve. This was conceived of largely as part of the breakthrough initiatives. So our team is hugely thankful to the Breakthrough Prize Foundation. And a lot of this started as a conversation around what we might be able to do kind of similarly to the other breakthrough initiative, Breakthrough Starshot, which is aiming to send micro-scale satellites to Alpha Centauri to take pictures of potential planets and send them back to us. Well, we might be able to achieve something similar with remote sensing just here from Earth. So Breakthrough Watch is attempting to achieve this through both imaging and other techniques, such as precision astrometry for nearby stars like Alpha Centauri. Alpha Centauri is the main focus currently, but certainly other stars are also in our list of ones that we find interesting. So Breakthrough Watch partnered with ESO, the European Southern Observatory, in order to carry out, or well, conceive of this NEAR experiment, rather to have the VLT participate in the Breakthrough Watch campaign. And a lot of people participated in this. Our team extends to, I think, around 40 or 42 people or so. A lot of people brought their expertise to this project, and well, it wouldn't be possible without them. So well, their names are all listed here. These are some of the people who are in charge of the NEAR leadership. So this picture was taken during commissioning. From left to right here, we have Eric Hansen from Paris, Ralph Siebenmorgen, Uli Kauerful, and Gerard Zenz, all at ESO, the NEAR leadership. And Marcus has been an awesome leader, and the NEAR experiment would be in for Marcus, so I can't Marcus was in this, and really all of the people were interact with and get to know all of. So experiment on the VLT. So scopes of the VLT, just one, this is a plume. UT4 is LT that has the deformable, which is an important component for the near experiment. Lets us perform adaptive optics without air, which will background, which we're trying to mitigate. Fennec AO may be a possibility for the feedback for another discussion. Oh, I think adaptive secondary is we can do. So this is the secondary mirror of the VLT on a bed of about 1,000 magnetic. I think that's also a pretty cool part of the technology. Not physically connected to the actual magnets.
Hi, Kevin. I think we are losing you sometimes. Excuse me to cut you off. We're losing you sometimes. So I'm wondering if we could maybe stop your video for a bit.
Sure. Okay. Okay.
Okay, let's try. Okay.
Tell me if I can switch to another. Okay, so another piece of which was important for the near campaign is so coronagraphy has been employed shorter wavelengths. This is a design for is widely in use today. Of it for use at 10 microns mass, and this is a annuli with about 10 roughly sub-wavelength spacing shown on the right, and with this characterization vortex wrapping around that once you've traversed 180 degrees, vectors cancel, and this creates a center of the image. The light from the star, and hopefully, and this optic goes to in some of these papers that I've listed below. In addition to that, we also use the deformable secondary mirror for another important purpose for the near campaign, and that's to perform rapid chopping. And by rapid here, I mean 10 hertz, which, well, maybe that's rapid or not, depending on what frequencies you're used to thinking about. But in terms of chopping with a secondary mirror, I think this is actually pretty fast and is about a factor of 2 beyond what the VLT could do before the near campaign decided to try to push this limit. So why we do this is generally to reduce the background. The background is coming from several different components here. There's, of course, the sky and the telescope and what I would call smooth thermal background. And then there's also the background from the instrument itself. And that's what you're seeing here is these stripes. Some of this is kind of regular, some of it, but another component of it, which is a little bit less well understood, is varying on timescales that are, of about 10 hertz. So that's the reason why we want to move the field over this short of a time frame so that we can take one image and subtract it from the other and get rid of these sources of noise that are coming from the telescope, sky, and camera itself. One thing that you might notice here that's a little surprising is that the star behind the coronagraph, whether it's Alpha Centauri A or B, and A is actually a bit brighter, but in any case, the star behind the coronagraph here actually shows up as brighter. And that's because the coronagraph itself diverts light from outside of the telescope pupil, partially diffracts light from outside of the telescope pupil back into the image center. You might think that this is, not at all what a coronagraph is supposed to do or how it's supposed to function, and that this would be detrimental to our overall performance. But it's actually not that big of an issue because the light is coherent and subtracts pretty easily. It's this nice smooth function rather than the speckles from the star itself that, create more of an issue. So, this can also be mitigated by putting a cold stop in front of the optic. So that would block out the light that would be entering from outside of the pupil. And this has been implemented on facilities like we have here at the LBT in Arizona, and this glow is significantly reduced or completely eliminated. But nevertheless, we're dealing with it with NIR. And by taking one image of alpha sun A on coronagraph and subtracting it from alpha sun B, this glow is mostly eliminated. More important than that, most of the noise from the detector and background is also largely reduced. And you can see here this high contrast region in the center where the coronagraph is, and where the residual of alpha sun A and B is also, although you can't see it in this stretch. You also see the off-axis PSFs of alpha sun A and B off to the sides. Yeah, I think that it's useful to just keep in mind what those are and where we're actually looking for planets in this image. So planets around alpha sun A here would appear as negative sources, and planets around alpha sun B would appear as positive sources. So we're looking for planets around both stars at the same time in the central regions of the image. We also utilize angular differential imaging, or ADI. So we let the astronomical field rotate with respect to the telescope pupil so that we can well, do something as simple as creating a mean over those images and subtracting them and then derotating so that we can further reduce this central coronagraphic residual. Over the course of the campaign, we collected about 5 million of these CHOP images, amounting to about 7 terabytes of data, all of which was made immediately public on the ESO archive. So if you'd like to go take a look, I encourage you to. We'd be really happy and excited if anybody can come up with more sensitive data reduction than ours. The purpose of this is really to be experimental and community endeavor. So I encourage anybody interested to go ahead and take a shot. Quickly here, just some stats of the campaign. Going after these sensitivities in the mid-infrared, we knew that we were going to have to incur long exposure times. Going to the sensitivity levels that we were aiming for in about the sub-Neptune range, we knew we were going to need about 100 hours, or rather, an observing campaign that was going to have to be conducted over multiple nights. So this occurred over May and June of 2019. I think it's a bit easier to look at in this way. So this is showing the cumulative observing time that we collected during the campaign. I was kind of surprised to see that it was actually this rather nice linear projection, or well, linear trend upwards, although of course we did lose some time due to bad weather, and well, we became a bit nervous during some periods, but ultimately we got close to our goal of accumulating 100 hours. And I think this plot is only showing the data that we deem to be of good quality, so we got a bit more than this. We did also take one night of data after the campaign. It's useful as a check of orbital motion for brighter planet candidates and systematic artifacts. But it was taken so far after the initial campaign that any orbital motion of planets in the habitable zone makes it a bit complicated to combine this with the other data. So this is what NIR saw. This is the full frame image on the left showing alpha sun A and B's off-axis PSFs that I showed you previously. This also shows some of the detector artifacts, which I want to explain to you in just a moment. But first, I should also say that the image on the right now is this blown up region of the habitable zone of alpha sun A, or well, alpha sun A and B. So here we see a positive source, which suggests that it might be something around alpha sun A. We don't see anything that looks like it could be a negative source around alpha sun B. And I should say we also are certainly not confident that we've actually detected anything around alpha sun A, just that this is a possible detection that we'll look more into a bit in a moment. But turning now back to the detector artifacts and things that I've indicated in the left panel here, these features 1 and 2 are actually some of the, well, more challenging things that we had to deal with in the campaign. What these actually are persistence that's accumulated during the chopping sequence. So while the deformable mirror is moving alpha sun A and B off and on the coronagraph, the camera's not exposing, but some photons are still hitting the detector and finding their way into the subsequent exposures. So that's what you see here, this dark line marked 1 and 2. And there are some other features that we understand in a bit more detail, that like this one, it's labeled 3 here, which is simply a reflection off of the filter. So we tried to come up with a model for each of these to remove them from the final image, and also just to get a handle on what we're looking at that might be systematics and might not be systematics. So let me walk you through the image panels here. And also, how's my internet doing? If you're not able to hear me, please let me know.
It's doing much better, Kevin.
Okay, good. So in the middle here, you're just seeing essentially the raw data. So this is the combined image. It's also been processed with ADI, but the persistence has not been removed. And on the left here, I'm showing an empirical model that we created to match this as best as we could. So this is essentially just stacking positive and negative lines on top of each other and then convolving it with the beam profile. And on the right is a more sophisticated model that we created by actually simulating the motion of the stars across the detector and also its response. In this version that I've shown on the top right, I've also processed with ADI so that you get a more one-to-one comparison with the image on the left. And on the bottom left and right panels, you're seeing each of these models subtracted. So the empirical model is subtracted after the fact. And you see it does clean up the image quite a bit. It probably cleans it up the most, which isn't really necessarily a surprise because this is the best fit that we could do just by eye. And on the right, you see that it's cleaned up, although not quite as much inside of the actual persistence stripes. I think that's, well, probably to be expected that our model can't match all of the subtleties actually and what's going on with the chopping here. But what's going on in this model on the right is that there's a small subpixel offset of about 1/4 of a pixel or less that leads to this difference in the persistence patterns. So if we could exactly replicate the chopping motion, then of course one chopped stroke's persistence pattern should roughly cancel out the other one. But when there's a bit of an offset, even something as small as a fraction of a pixel, we end up with this kind of multi-line pattern. And subtracting off this model before doing the ADI actually has a benefit for the rest of the image area and not just the areas impacted by persistence. So if you look at the bottom left and bottom right panels here, you notice that the model that's subtracted after the fact results in a higher background in the rest of the image areas. And that's because the persistence pattern rotates with the field of view and ends up biasing the angular differential imaging or PSF subtraction that we attempt to do later on. So by removing this model from the data at an earlier step before we perform ADI, we actually clean up some of those other image areas. But nevertheless, we still can't really clean up the areas impacted by persistence to the level where we're confident assessing any of the features or sensitivity within here. So for the subsequent analysis, we just eliminate, or well, rather don't consider anything in between these dashed lines. Okay, I've turned my video back on also. Hopefully it doesn't wreck the quality, but if it does, just please let me know. All right, so this is how we assess the sensitivity of the near data, is by injecting planets, well, signals of approximately planetary brightness and trying to recover them from the data. Again, we don't consider anything in the regions that are lost due to persistence. So unfortunately, our, well, assessing the sensitivity of exoplanet imaging is already limited by small sample statistics, because the way that it works is that you're comparing this one beam diameter and the flux within it to the other possible beam diameters of that separation and the flux within those. And you can see that there are only so many samples available at each radii. And well, it's unfortunate that we are dealing with even smaller sample statistics because we have to lose some area due to the persistence, but that's what we're dealing with. So these examples show essentially what point sources would look like that we're able to inject and recover in the data. And the example on the right here is showing a source that would be really stretching our sensitivity limits. So something that might be identified among the other speckles in the data, or other noise, well, positive sources within the noise, but not something that we would be confident enough to say this is likely a detection. So this is showing those injection recovery tests in more of a graphical form. So the solid line here is showing the 3 sigma, or sorry, the signal to noise ratio of 3, or where the brightness at which each of these sources that's injected is recovered at a signal to noise ratio of 3. We use SNR here instead of trying to refer to sigma or Gaussian based statistics because We're well aware that our underlying noise distribution here is very likely non-Gaussian. It certainly is if we include the persistent stripes, and there's still some impact of these throughout the rest of the data. So we're not trying to make any analogy or utilize any assumptions of Gaussian statistics to link to false positive ratio or probabilities or anything like that. We're simply saying that this is the brightness at which we inject something, recover it at 3 times the standard deviation of the other noise apertures. The dashed line here simply shows the contribution here from the background pixel to pixel noise if we measure this far away from the star. So you can see that we have quite a bit of additional background. Some of this comes from the coronagraph and the star itself, and also we're contrast limited as we go to smaller separations. Now, to explain the models that are in the back, the red lines are showing planets with assumptions that their temperature is about 50% higher than it would be for radiated equilibrium, which is the rather extreme value that's motivated by Neptune in our own solar system. So Neptune's Neptune's temperature is actually about 50% higher than it would be based on assumptions of equilibrium. But of course, it's out also at 10 to the AU. So raising its temperature by 20 Kelvin is quite a bit less extreme probably than raising the temperature of one of these planets. So the blue lines probably correspond to more realistic values for what we would expect planets with roughly Earth-like conditions for additional heating and albedos to look like. And the takeaway here is that for Alpha Centauri A within the habitable zone, our sensitivity limits are extending beneath what would be assumed for a cold Jupiter or Saturn-sized planet, and even beneath what would be approximately a warm Neptune-sized planet. So compared to exoplanet imaging sensitivity limits, which are typically limited to super Jupiters at wide separations of tens of AU, here for the first time, I think we've actually pushed down beneath the scale of solar system planets within the habitable zone of a nearby star, which I think is pretty exciting. The plot on the right here shows all of the same things, but for Alpha Centauri B. Alpha Centauri B is about 30% fainter. Its habitable zone is a bit closer in, and its planets would be at colder temperatures also. So our sensitivity there is not quite as great. There we're really only sensitive to warm Jupiter or Saturn-sized planets. So of course, that's what we would detect if it were in that position currently, but planets orbit and won't always be at the same projected separation. So we ran a Monte Carlo simulation over possible planetary orbits and used that to assemble these completeness maps. Again, on the top here, I'm showing planets that would be about 10% brighter, or sorry, 10% warmer than they would be in equilibrium. And on the bottom is this more extreme case that's similar approximately to that of Neptune. And what I find exciting here is that if we look at the contours that are 0.6, 0.5, these extend down to beneath Jupiter and Saturn sizes. So this campaign would have about a 40% or so chance of seeing a Saturn-sized planet if it were in the habitable zone under not very extreme assumptions. Now, if we were to push these assumptions to the extreme and say what might we have seen in the absolute most favorable case, that's what would be shown by this plot on the bottom here. So around Alpha Centauri A, which we have a bit better sensitivity, and if we assume that the planets are as bright as we're comfortable assuming that they might be, we would maybe have about a 1 to 10% chance of seeing something that would be like a warm Neptune-sized planet, or maybe a bit smaller than that. But again, that's kind of stretching it to the extreme. So taking this more realistic completeness map and comparing it now to the results of a recent exoplanet imaging survey. This plot on the right is the results of the GPIS survey. So this is a survey of about 300 young stars, taking up about 200 hours of telescope time. And the way that you read this plot, which has mass on the y-axis and separation on the x, is that you can just take a region of the plot and the number of detections there and use that to read off a rough occurrence rate. So for instance, here there's 1 detection, say in this 16 star region, so, or say 2, so the occurrence rate here would be about 1/8, or 1 out of every 8 of these stars has one of these objects. So where does our sensitivity fall into a plot like this? Well, what is exciting to me about this is that this is in a region where GPIs and all of these previous exoplanet imaging surveys and experiments don't have any sensitivity at all. So this is really right down at the origin where all of these previous attempts would have been completely blind to planets. And this is mostly a result of the distance. So alpha sends, of course, at 1 parsecs. The average distance to the GPI's targets is 30 to 50 parsecs. Yeah, so this really largely reflects the age, and also that we spent 100 hours on a single target rather than 200 hours split over 300. And also that our observations are sensitive to the wavelength ranges in which these colder planets would be brightest. But yeah, so I think that this is a pretty cool result that we're now enabling sensitivity down here in kind of the corner of this plot. All right, so that essentially takes care of all of the results that I'll say are robust from the NEAR campaign. So I'm going to turn now to some of the things that are we're still working on and that we're a little bit less certain on, but I think are also potentially pretty exciting. So let me take a moment first and say that if you've seen some of this in the news the past week, there's a good chance that you've seen a story that was significantly overstated. And I apologize for that. We kind of knew that this was going to happen, that if we say there's a planet candidate in the habitable zone of Alpha Centauri, that we're going to get some articles like the one on the left that say that, well, we've already gone ahead and discovered this. And well, I'm sorry, that's not the case. Thankfully, a lot of articles did espouse proper skepticism, like this one on the right here. That starts off saying, is it a planet? Calls it a candidate. It says it might be a mirage. So thankfully, a lot of the press actually did get the story, well, I would say correct here. Yeah, so with that preface that we're totally not sure that we've seen anything at all around Alpha Centauri, let's go ahead and look into this in a bit more detail. So this is why I say there's a chance that we might have seen something that's interesting. So the signal that I showed you previously and indicated as C1 or candidate 1 has some properties that makes it look pretty stable. So one is that it's present in independent data reduction. So this image on the bottom left shows processing from 2 completely independent pipelines. One major difference is that the one on the left removes artifacts. The one on the right has no systematic artifact removal. So the persistence stripes are there, but also, in addition, some of these reflections from the NEAR filter are there. So these are simply just reflections of the primary star or alpha Cent A and B that have been removed in the model on the or image on the left. But nevertheless, the important point is that this kind of weak signal or region of flux here is present in both images. In addition to that, in both of these pipelines, it's present in various reduction parameters. So it's not some cherry-picked source that, well, you could say is a speckle that's been gardened or something like that. So I think those are good tests, but it still doesn't tell us whether or not this could be something that's just a random positive within the noise, or, well, rather a random false positive. These images on the right address that possibility. So like I said before, we can't really translate the signal to noise of this detection into a false positive probability or true positive probability or something like that, because we don't know the underlying noise distribution. But what we can do is we can split the campaign into multiple epochs. Here on the top left, the first half, and on the top right, the second half, and on the bottom, odd nights and even nights. So completely independent subsets of the data, and the detection is still there. Its signal to noise is about 2, a bit like 2.2, 2.3 in each of these images, and it grows up to about 3 in the total campaign. So it grows with about the square root of time, as we would expect. And moreover, it's rather unlikely that we would see a random false positive in the same place on multiple nights. So we're pretty confident that what we've seen here is, well, something that is an actual signal. Whether or not that's a systematic signal or systematic false positive, or whether it's something astrophysical, that still remains to be addressed. So these are the 3 possibilities that I just mentioned. Well, of course, it could possibly be a planet. Certainly seems like it could be a point source, but Similar to our own sun, alpha Centauri might also have warm dust in its habitable zone, and with a bit more mass than our own solar system has, possibly this exozodiacal dust around alpha Centauri could manifest as a point source with some special properties of the disk. Or it could just be a systematic artifact, or perhaps something else that we haven't thought of. But the one thing that we can rule out is that this is not a background object. So images that were taken in 2009 of the field that alpha Centauri currently inhabits show that there's just no object there with a brightness that could explain what we're seeing. Certainly no star could explain it. For a background galaxy, we could explain this if it's one of the most rare types of galaxies that happens also to be projected right behind Alpha Centauri A. So rather, if this is a Z of 10 galaxy, of which Hubble only found a few of in the whole sky, if that happens to be right behind Alpha Centauri A, which is pretty unlikely, then that could explain it. But we think that's sufficiently unlikely that we're willing to rule out both the background star and background galaxy hypothesis. So we're left with these other three, which are perhaps it's a planet, perhaps it's a disk, or, well, perhaps it's just some systematic artifact that we don't yet understand. I already showed you some images of simulated planets, so I don't think there's too much extra to take away from this slide other than, well, this is what point sources would look like in the data. And here I've shown them to you next to C1, whereas previously I hit C1. So here you can see it more of a one-to-one comparison. The disk possibility, though, deserves a little bit more discussion. So just from the brightness of the planet, simulated planets, we can come up with some properties that could explain C1. So it could be a 3 to 7 Earth radii planet at 1.1 AU. And this image in the bottom left panel here shows such a model subtracted. On the top right here, we've created an image of an exozodiacal disk and tried our best to get this to match the properties of C1. So since we only see something on one side of the star instead of the other, there has to be some sort of asymmetry going on here. So to start off, we fix the inclination of the disk to that of the binary. We think that's a pretty fair assumption to make, something like a 70-degree or 80-degree inclination or close to edge on. And then also by setting up a grid search of parameters and trying to minimize the residuals in this bottom image, we extract out both the mass of the dust and also the eccentricity of the disk that would be needed to explain this geometry and brightness. And what we end up with is something like 60 zodies of dust. So 60 times the amount of sun, or the amount of dust that the sun has, which might seem quite like a lot. It's certainly higher than 95% of sun-like stars, as the host survey told us, but it wouldn't be unprecedented. Also, as the host survey told us, Epsilon Eridani has about 200 zodies of dust. So 60 wouldn't be outside of the realm of precedent, but it would be large. The eccentricity, on the other hand, could also possibly be explained because the binary itself has an eccentricity of about 0.5 and a semi-major axis, or well, an orbit that brings it to within about 8, well, the stars to within a periapsis of about 8.5 AU. So in that configuration, we think that the binary could excite this non-zero eccentricity of the disk. And well, it's hard to say which of these possibilities is more or less likely. And certainly there's still room for this third one here, that this is just an artifact that we have, well, at present, a poor understanding of. I think the message of this slide is pretty quick. Simply suffice to say that if we convert the radii that we that are consistent with the brightness of C1 to a mass, using a mass radius relation, then this would be still consistent with the radial velocity detection limits for Alpha Centauri A. So in the habitable zone of Alpha Centauri A, Zhao et al. 2018 placed limits of about 50 Earth masses in the habitable zone of Alpha Centauri A. So that rules out some of the upper range of, say, 7 to 9 Earth radii that could have potentially explained this signal in the imaging. And there's still a range in here of about 10 Earth masses to about 50 Earth masses that could be consistent with both the RV non-detection and detection in the imaging data. So where do we go from here, and how do we follow this up and see if we potentially saw something? So I think there's lots more work to be done with the VLT, both with NEAR, also another imaging campaign, and possibly radial velocity with Espresso. JWST will also be a very sensitive mid-infrared imaging instrument that should be online in the near future. That I'm aware of some plans to follow up AlphaSen and see if whether or not we've actually seen anything with James Webb. Another possibility, and one that I'm excited about, is precision astrometry. So another component of Breakthrough Watch is a dedicated space telescope to monitor AlphaSen A and B, simply monitoring their positions over time and looking for the reflex motion from a planet orbiting them. I've heard some people say that this might be possible with ALMA also. I haven't thought this through all the way, but I think it's an interesting possibility that I wanted to also mention for the ALMA experts here to think about, that maybe we could get precise astrometry on AlphaSen A and B and see and get an answer on this in the near future. So that's essentially the conclusions from what we've done so far. I want to go through this quickly because I also want to talk about what we want to do in the future. So we imaged AlphaSen for about 100 hours. This is essentially the longest exoplanet imaging observation that's been attempted, and also one of the first in the mid-infrared at 10 microns. This allowed us to establish new sensitivity to planets that would be beneath the sizes of those in the solar system within AlphaSen's habitable zone. And there might or might not be something in the data that needs to be followed up. I don't know really what else to say about it right now other than that. And there's lots of data out there, so we're hoping that other people have fun playing with this. And again, I can't thank everybody involved in this experiment enough. It wouldn't be possible without these people. All right, so with that, where do we go from here, and what are the lessons that NIR has taught us for the future? So to start off, James Webb is going to be probably one of the things that brings mid-infrared exoplanet imaging into the mainstream in the near future. Although unfortunately it wasn't designed with exoplanet imaging in mind, it was going to have a relatively poor inner working angle. So while James Webb might give us an answer for whether or not there's anything in the habitable zone of AlphaSen, it's going to be rather challenging to use James Webb to image, say, other nearby sun-like stars, just because its beam, well, its angular resolution is, well, not fine enough so that we can see these very faint planets at very small separations from their stars. Working from the ground, the LBT here in Arizona actually has a system that's already pretty similar to NIR. We have a very similar mid-infrared camera. The detector itself is almost identical. We have two 8.4 meter mirrors, which we can focus on the same detector, and each of them is equipped with an adaptive secondary. So it's already quite similar to NIR. And something that I'm excited about is simply where the LBT is located. Unfortunately, it can't see AlphaSen, so this isn't a great instrument to follow up the results of NIR, but for imaging other nearby stars like Sirius, etc., the LBT's position on an inland peak, rather than right next to the Pacific coast, enables it to, not all the time, but sometimes experience these colder winter temperatures that lower the ambient temperature also, well, lowers the ambient temperature and lowers also the temperature of the primary mirror, which results in about a 25% reduction in background. So that's one advantage right off the bat. Also, of course, having two mirrors lets us, well, collect twice as many photons. So if we put all of this together, and also some of the other aspects of the LBT that we think will allow us to push a bit deeper, we expect we'll be able to get about 2.5 times deeper than NIR's background limit. So compared to, well, if we were to look at simulated exoplanets around Sirius, this would push us from about the Uranus or Neptune size down to hopefully about the super Earth size. So this is one of the plots that I put into my Hubble Fellowship proposal, and something that I'm excited to be working on today. This is some of our preliminary data that we got. The image on the right is actually some of our first on-sky data for Tau Ceti. This is another nearby sun-like star, actually the closest single sun-like star. And I've put in a simulated planet here. This is much brighter than anything that would actually be possibly a planet, but I had to pick a pretty high brightness because the system was warm and not cryogenic. So we think we can go quite a bit deeper than this, in other words. On the left is showing the reduction from implementing fast chopping at the LBT. And we get a similar reduction by pushing from about 4 Hertz to 10 Hertz is near good. So something like a 40–50% increase. And something that I'm really excited about doing this on the LBT is that we don't have to use the AO system to chop. We use the LBTI's internal beam steering optics that would usually be used to combine the beams in order to do the chopping. So we don't have to pause the AO system or do anything like that, which incurred some additional well, created some additional challenges for near. We think we can get around those with the LBT. So if we're able to achieve near-like sensitivity around a handful of nearby sun-like stars, what sort of discovery space might we open up? And that's shown here on the left in this blue region. So currently directly imaged planets or regions of parameter space where we might directly image planets are shown in the green. Again, these are primarily super Jupiters on wide orbits, but if we can routinely achieve near-like sensitivity for sun-like stars, we can probably push down the Jupiter-like planets around, say, 10 to a dozen nearby stars in the near future. And these gray points here are showing that these planets do exist. These are planets that have been seen in transit and RD surveys. So nature is, well, capable of making planets like this to be detected. And if they exist around one of the stars in the solar neighborhood, then we hope to be able to image them in the near future. So I want to leave you with a bit of a vision for the future of extremely large ground-based telescopes. And there are a few different scaling relations that I could put up here that are important here. Some of the more obvious ones are, well, of course, we get more light from the planet going as the square of the planet's radius itself. Also, the planets are getting fainter by the square of their distance away from us. But probably the most important scaling relation for the ELTs is that the time to achieve a specific signal to noise ratio scales as the -4th power of the diameter. So what took us 100 hours with an 8-meter telescope will take us much, much shorter with an extremely large telescope. So we hope to be able to image planets in the habitable zones as small as Earth-like planets around Alpha Cent in simply a matter of hours. And I've heard some more optimistic estimates than that even, but I think hours is a number that I'm comfortable with. So what does that let us do? This plot here is showing the approximate brightness, or again, in contrast units of an Earth-like planet if it were at the outer edge of the habitable zone around a handful of nearby stars. So the colors here are showing the approximate colors of the star. The size of the source shows how bright the planets would be. But really what's important to pay attention to are the values that are on the axes, which are the contrast and the separation. So right now, if we're able to achieve ratios something like 10 to the -6 at about an arcsecond, Alpha Cent A and B are really kind of the only targets that fulfill these criteria and the best ones for us to go after at the currently today. But in the future, we hope to be able to expand this circle to enclose all of these targets here. So soon in the near future, with the LBT, we hope to be able to target Sirius, whose planets would be a bit fainter, but a bit further out. And with the ELTs, we'll be able to go after nearby sun-like stars like Tau Ceti, Epsilon Arri, and a handful of others. So this is something that I'm really excited about because, well, of course, if we're able to observe more stars, then we're able to potentially find and study more planets. Okay, I have a couple minutes, so let me come back to my summary in a second here, because I also want to talk about this bonus slide, which I'm really excited about. So I haven't said anything at all about characterizing these planets yet. And of course, that's something that we want to do once we're able to detect them, is to learn more about them. This is an image of Jupiter taken with NIR in the mid-infrared, so, or actually in the same filter that we're using here, this N-band or 10 to 12.5 micron filter. And what you see here is, instead of just a boring unresolved surface or unresolved image of an exoplanet, you actually see the resolved surface of Jupiter. So you see these features that are brighter and darker. You see the equatorial bands and jets and different features in the atmosphere, storms, etc. In the future, if we want to learn something about the planets that we detect in the mid-infrared, I think this is a good example. So what are we going to get from these planets? Well, the mid-infrared gives us, in bulk, a combination of information on the planet's temperature, its radius, and its separation from the star. There's also, of course, a lot more going on in that, like on the surface of Jupiter here, but that's essentially what we're going to get. In order to break those degeneracies, we're also going to need other methods, like, say, radial velocities to actually get the masses, reflected light to get the albedo and the temperature, and we're going to have to follow these planets in their orbits to be able to break this degeneracy between, well, how far away they are and what their temperature is. So that's where I think this is heading, is that mid-infrared imaging can give us some very important information about the planet's atmospheres, but really where the power is going to come from is these multiple method techniques and approaches. Yeah, so just to summarize and conclude, this question that I started off the talk with of how close are we to imaging a second Earth? Well, we're not quite there yet, but I hope that I've convinced you that we're quite a bit closer. And a lot of this, I think, was demonstrated with NEAR. And one of the more exciting things that I think NEAR demonstrated is that the ELTs in the future are going to be able to really be game-changing in terms of imaging low-mass planets in the habitable zones of nearby stars. So thanks for your attention. Sorry I only left a few minutes for questions, but I'm looking forward to any questions or discussions that you have.
All right, thank you so much, Kevin. First question is from Don McCarthy.
Hi, Kevin, thanks. That's very interesting stuff you're doing. I was wondering, based on my old chopping days, if you see an offset difference between the two directions due to changes in the thermal background itself.
Do you mean an offset difference in if we chop left and right or up and down?
A systematic, like a DC level change. I don't think the secondary is undersized, right? So as you chop it, presumably the beam is scanning across subtly different temperatures in the telescope or the spiders or the housing of the secondary.
I see. Yeah, I don't know off the top of my head how big that offset is. I agree that we're probably observing some offset there. We also use a high pass filter to remove any smooth background that's left after we do the chopping. So perhaps that also helps to take off some of that offset.
Thanks. This could also be another advantage of LBT in that I think the secondaries are undersized.
Mm-hmm.
All right, next question is from Yanni, who asks, do we know how the mid-infrared sensitivity with JWST MIRI compares to NEAR's current capabilities, both the coronagraphic narrowband and non-coronagraphic broadband imaging? Would the coronagraphs have the sensitivity needed, or would you need to do some really careful reference differential imaging with the non-coronagraphic broadband filters? So I know that was long. If you need me to repeat part of it, I'm happy to.
Yeah, I think I got it all. So, but if I don't answer anything, please remind me the part that I didn't answer. So James Webb, I think, is going to blow NEAR out of the water compared in terms of just what its background limit is away from a bright star. I don't actually know what that difference is, but I expect it to be pretty huge. Now, the second part of the question is what James Webb will do in terms of contrast limited performance in the mid-infrared. For Alpha Cent, it should come pretty close. Now, it also depends on how much time you expose for. So I expect that if we were to conduct a similar length experiment with James Webb as we did with NEAR, so give James Webb 100 hours of exposing time for Alpha Cent, that it would probably come up with a better limit at 1 arcsecond than we did with NEAR. But of course, 100 hours with James Webb is quite a bit more expensive, and I think always from the ground with a high-powered coronagraph, we're going to be getting better inner working angles.
All right, next question is from Mark Marley, who asks, are you assuming T equals effective temperature in the search limited plots because of absorbers at 10 microns? Our models show that for Gyrians, the temperature is usually smaller than the effective temperature at N band.
Yeah, so we're using the, sorry, can you repeat the first part of the question?
Yeah, are you assuming that the temperature equals the effective temperature in the search limit plots?
Are we assuming that the temperature equals the effective temperature?
The brightness temperature specifically, does it equal the effective temperature?
I'm not sure. I'd have to think about that. So yeah, off the top of my head, I'm not sure.
All right. Any quick final questions for Kevin?
You can just raise hand and directly ask question right now.
Yeah, it doesn't have to be in the chat.
Right.
All right. I'm not seeing anything. though Jaren points out that there is a archive paper about anticipated sensitivity of JWST MIRI for anyone interested. But other than that, thank you all for coming. Thank you, Kevin, for a really interesting talk, and we'll see you all next week.
Yeah, thanks everybody.
Thank you, Kevin.